In the previous lecture, it was mentioned that the need to compute the area of tracts of land was the reason for the genesis of geometry as a science. Much time was spent developing formulas for the area of various two-dimensional shapes. One of the earliest recorded geometry problems is a challenge to find a square whose area is equal to the area of a given circle. This problem is even mentioned in the play The Birds, written by Aristophanes in 414 BC. Because of the unique shape, the circle's area was a goal of many philosophers. It was understood that the ratio between the circumference and the diameter of a circle was a key piece of knowledge. As we have seen in a lecture on irrational numbers, the ancients believed that the ratio could be written as a fraction, but we know it cannot. In 1800 BC, the Babylonians used 3 1/8 for this ratio, while in 1650 BC, the Egyptians were using a number we would write today as 3.16. In the 3rd century, Archimedes used a polygon that was inscribed in a circle, which was then inscribed in another polygon to estimate the ratio. He estimated this ratio was between 223/71 and 22/7. He was accurate, but he did not have a particular number because, as we've seen, there is no fraction you could write for the ratio between the circumference and diameter of a circle. In 480 AD, Zhu Jiangzi of China defined the ratio that we call pi as 355/113. If you divide that fraction and make it into a decimal number, you get 3.1415929, which is correct to 6 decimal places. And again, that was in the 5th century AD. Indian mathematicians, whose names were Arbata and Bhaskara, who Arbata was in 530 in the 6th century AD, Bhaskara in the 12th century, produced more accurate rational representations of pi. But again, they did not have a precise representation because it is an irrational number. In the 17th century, Johannes Kepler wrote the formula for the area of a circle as 1/2 times the radius times the circumference of the circle. Again, people were seeking a formula for the area of a circle. The formulas for the area of some common polygons started with the square, and the formula for one type was used to find the next formula. Let's take a look at a few of these shapes. The obvious shape to start with is the square. The square is the basic unit of area. How many unit squares can one fit on a surface is the area of that surface. The number of unit squares that can fit in a square whose side measures 5 is obviously 5 times 5. You can see in the square, we have divided the square up into unit squares. Each of those squares is 1 unit by 1 unit. And there are 5 of those squares across, and each column has 5 squares from bottom to top. And 5 times 5 is 25. So we say that the area of that square is 25 square units. The area of a square is obtained by multiplying the side by itself, or squaring the side. In this case, 5 squared is 25. Angle measurements were necessary for many of these geometric shapes, and there's evidence that the Egyptians had sundials as early as 1500 BC. Knowledge of angle properties must have been known to them in order to be able to create the sundials. And those angle properties were then used to deal with the various polygon shapes. The use of the word square, commonly used for the second power, is due to the fact that the formula for the area of a square is the second power of the side squared. A rectangle is a more general shape than the square. We look at a rectangle whose length is L and whose width is W. And again, the question is how many unit squares are to be found in the surface of that rectangle. All we have to do is recognize that we have L squares across the bottom, and each column of squares has W squares up from the bottom, and therefore the total number of squares in a rectangle whose length is L and whose width is W is L times W, the area of a rectangle. Now we take a parallelogram, and you'll notice we start off with a parallelogram in this picture, the solid lines. A parallelogram has four sides, opposite sides are parallel, and we take a right triangle and remove it from the left side of the parallelogram and add it on, that same right triangle, to the right side. That is done using those dashed lines. And we find that we have a rectangle whose length is equal to the base of the parallelogram, and a rectangle whose height is the same as the parallelogram. Since we have not changed the area of the figure by cutting out and repasting that right triangle, the area of a parallelogram is the product of the base and the height. It is interesting to note that the area of a parallelogram does not vary as we vary the base angle, provided the base and the height stay the same length. Okay, so therefore we have a formula for the area of a parallelogram based on the formula for the area of a rectangle, based on the formula for the area of a square. We now take a look at a triangle. And if you take any triangle, any shape, and we'll talk about specific types of triangles in the next lecture, and you take that triangle and flip it over on any side, you discover that the new figure you have, as shown in the picture, is a parallelogram, which means any triangle you find is exactly one half of a parallelogram, whose base is the base of the triangle and whose height is the height of the triangle. Since there are two of those triangles in one parallelogram, and since the area of a parallelogram is base times height, the area of any triangle is one half the base times the height. And I might recall that the height of a triangle is the distance from the vertex at the top to the base that is perpendicular to the base. And we'll talk more about this, which is sometimes called the altitude, in the next lecture. A trapezoid, which is a four-sided figure with one pair of parallel sides, is made up of two triangles. If you draw a diagonal from the lower left corner, for example, as we have, to the upper right corner, we can see we have two different triangles. But each of those triangles have the same height. The distance from the base at the top to the base at the bottom is the height for both triangles. They obviously have different bases, labeled B1 and B2. Therefore, the area of the trapezoid is the sum of the area of the two triangles. 1/2 B1 times H plus 1/2 B2 times H. To write this formula more simply, we simply factor out the 1/2 and the H, and we have that the area for any trapezoid is 1/2 the height times the sum of the bases. Formulas for the volume of most three-dimensional shapes were much harder to discover than the formulas for the area of two-dimensional shapes. The onset of calculus allowed the discovery of these formulas to be accelerated. The volume of a cube and the volume of a rectangular prism or box were easy to find. Other figures presented a much greater challenge. Archimedes used his method of exhaustion to find the volumes of various solids. As I've mentioned earlier, Archimedes is one of my heroes. He's one of the great minds of the ancient Greek world, and I sort of consider him the Ben Franklin of the ancient Greek civilization. Besides his mathematical discoveries, Archimedes, while sitting in a bathtub, discovered that bodies are buoyant in water, and depending on the weight or the mass of the body, that indicates how far the body sinks in the water. He used this to discover criminals who were cheating the king of money because they were charging the king to make crowns and stealing gold from the crowns and making the crowns out of gold and silver. And Archimedes was given the task to see if these people were cheating and to catch them. And what he simply did is he took the weight of gold to make a crown and sunk it in water, took the crown and sunk it in water, and saw that the levels of the water were different, indicating that the mass of the crown was less than it should be, and therefore a baser metal, silver, had been substituted for gold. I believe those people were then killed, and Archimedes was rewarded. He also was a military genius, but indeed he was killed by a Roman soldier because the Roman general who had finally conquered his city wanted to see Archimedes, and Archimedes was too busy doing a math problem in his sandbox, and that's how they did math problems in those days, and the soldier got perturbed and gave him a spear which killed him. Archimedes is well known today, and as far as I'm concerned, if I was asked to invite a few great people who have died to dinner, Archimedes would be one of those, provided either I could speak Greek or he could speak English. But it took a long while to develop some of these formulas, as I said. Archimedes' work, as we said earlier, was lost for many, many hundreds of years to European scholars. In 1615, a serious attempt began to look at the volume formulas of various figures. In that year, and here's an interesting example of how we are motivated to find things, Johannes Kepler sought to find the volume of a cylinder. Why? Well, because he had concern that he was being cheated in the costs of casks of wine that he had purchased for the celebration of his second marriage. Kepler attempted to measure the volume of these cylindrical casks using thin layers as he went from the bottom to the top of the barrel. He needed the derivative to complete his work, but of course, this being 1615, it was yet about 60 years or so before the derivative was made known, and therefore he couldn't figure it out. But it was a beginning on the volume of the cylinder. Using calculus, it is simple to determine that the volume of a cylinder is equal to pi r squared h. That is pi, we know what that is, r being the radius squared multiplied by itself times h, the height of the cylinder. In fact, a more general formula for a prism is the area of the base, capital B, times the height of the prism. A prism is simply a three-dimensional object that has two bases, a top and a bottom, you might suggest, and the sides are rectangles. In the case of the cylinder, the bases are circles. In the case of the rectangular prism, the bases are rectangles. So therefore, we now can find the volume of any prism, as long as we know the area of the base and we know the height. Once the volume of a prism was known, the formula for the volume of a pyramid was easily obtained. The initial investigation of the volume of a pyramid was done in ancient Egypt. In 1650 BC, the Egyptians demonstrated that the volume of a square-based pyramid was 1/3 the volume of a square-based prism with the same height. Same height, same base. Again, a pyramid has one base and has a vertex at the top, while the prism has two bases. And the difference in the volume was that the volume of the pyramid was 1/3 the volume of the same size prism. Calculus allowed the generalization that the volume of any pyramid is equal to 1/3 the volume of a prism with the same base and the same height. Archimedes did discover the formula for one common shape, and that is the sphere. And Archimedes proved that the volume of a sphere is 4/3 times pi times the cube of the radius. 4/3 pi r cubed. Now, our next discussion in this lecture has to do with the polygon. A polygon is a closed figure with line segments for sides, all of which are attached to the adjacent sides at their endpoints. In a convex polygon, a line segment connecting any 2 points in the interior of the polygon is itself totally within the polygon. A regular polygon, that's a term I will use quite a bit, a regular polygon has congruent sides and congruent angles, congruent meaning exactly the same. So a regular 5-sided polygon would have all 5 sides and all 5 angles identical. The polygon with the smallest number of sides is the triangle. As we increase the number of sides by 1, we add one more triangle, adding 180 degrees to the sum of all the angles in the interior of that polygon. Let's take a look at a table of the sides and the angles in regular polygons. We have a table here that gives us the number of sides, the total of the interior angles, And we know every time we add a side, we add 180 degrees. And if we divide the total of all the angles by the number of sides, we get the measure for each angle, since all the angles are the same. Notice that for a triangle, 3 sides, 180 divided by 3 would be 60. So an equilateral or regular triangle, all 3 angles are 60 degrees. A 4-sided figure, a quadrilateral, has 360 degrees. If it's regular, we divide 360 by 4 and get 90. A square, of course, has 4 90-degree angles. And notice, as we increase the number of sides, we increase the measure of each angle, but each increase is less than the previous. From 60 to 90, from a triangle to a square, it increases by 30 degrees. From 4 sides to 5 sides, it increases by 18 degrees. And then by 12. And we continue to increase the measure of each angle as we increase the number of sides. Notice that a 20-sided polygon has 3,240 degrees, and each of its 20 angles is measured 162. From our discussion previously about limits, we can see that if indeed the difference of each angle as we progress the number of sides that difference is getting smaller and smaller, we should be reaching a limit. And of course, the limit is 180 degrees. And the limit of an infinite side polygon would be a circle. So if you look at a 100-sided polygon or a 200-sided polygon from a distance, it looks as if it's a circle. And a circle would have an infinite number of angles, each one 180 degrees. Algebraically, the measure of one of these angles in this regular polygon would be given by a formula, 180 degrees times n minus 2 over n. The 180, we add a triangle each time we add a side. N minus 2, the subtracting 2, it takes away the first 2 sides, so therefore a triangle, 3 minus 2 would be 1. And we divide by n the number of sides to get our single angle. All of the angles are the same since this is a regular polygon. Our next task will be to find the sum of the exterior angles for a polygon. Noting in the picture we have here, we have the interior of a polygon, and we've extended the side outside the polygon with a dashed line. The angle between that dashed line and the adjacent side of the polygon is the exterior angle. The interior angle and the exterior angle form what's called a linear pair. You'll notice that if you add those 2 angles up, you get a straight line, or 180 degrees. So if we know the interior angle, all we have to do is subtract 180 minus that interior angle, and that gives us the exterior angle. So here's another table. Again, with regular polygons, various number of sides or number of angles. Remember, in a polygon, the number of sides and angles are the same. And we have the interior angles we already know about. Notice the 20-sided figure still is 162. But now we've subtracted 180 minus the interior angle measure to get the measure of the exterior angle. 120 for the triangle, 90 for the square, 45 for the regular octagon, 18 for the regular 20-sided figure. And then if we multiply the measure of an exterior angle by the number of angles, we get the total of all the exterior angles dealing with that polygon. We see something quite interesting. All the numbers are 360. So no matter how many sides you have in a polygon, be it regular or not regular, the sum of all the exterior angles will always be 360 degrees. Our final analysis of polygons involves the number of diagonals, and this will lead us to our next investigation of geometric representation of numbers. But let's take a look at these diagonals. Remember, a diagonal is a line segment that connects one vertex of a polygon to another vertex of a polygon by going through the interior. So the sides of a polygon are not diagonals. Here is a table. We have 3, 4, 5, and 6 sides in our polygon, and the number of diagonals. Obviously, there are no diagonals in a triangle. There are 2 diagonals in a square, or any 4-sided figure. There are 5 diagonals in a pentagon and 9 diagonals in a hexagon. There's a definite pattern to the sequence of numbers of the total number of line segments. That is, add the number of sides to the number of diagonals, and the number of line segments, 3, 6, 10, 15. The pattern we observe has a name we've talked about. In fact, these are called the triangular numbers. And they are one of a number of types of numbers called figurate numbers, numbers which are associated with geometric shapes. And these shapes and the numbers and the pattern of those numbers have fascinated people for centuries. We will take a brief look at the triangular numbers, the square numbers, and the rectangular numbers and see how the geometry relates back to patterns and even to our knowledge of arithmetic. 6 is a triangular number, since we could have 3 dots on the bottom row, 2 dots, and then a 1 dot on top, as you can see. Now, if we take and add a row of 4 dots, we now have a triangle which is 10 dots. And again, the next triangular number after 6 is 10. The sequence of triangular numbers shown here, 0, 1, 3, 6, 10, 15, 21, etc., goes on forever and ever. The number is getting progressively bigger. The sequence is obtained, obviously, by adding the next number. So from 0 to 1, we add 1. From 1 to 3, we add 2. From 3 to 6, we add 3, and so on. The geometric picture shows us that, and looking at the pattern of the sequence of numbers shows us that. Taking another look at those numbers, if you add any two adjacent triangular numbers, you will always get a square number. So 28 plus 36 is 64, which is 8 squared. 45 plus 55 is 100, which is 10 squared. Triangular numbers were first identified as a sequence by Nicomachus of Gerasa, which is a town, I guess, in Greece. And he did that in 100 A.D. The square numbers are obtained by multiplying a whole number by itself. That is, numbers without perfect squares. A square number of dots can be arranged in rows to form a square. The sequence of square numbers shown here is 0, 1, 4, 9, 16, etc. And these numbers can be represented geometrically by a number of dots arranged in a square. So here we have 3 squared, the square number 9. And you'll notice if we want to get the next square number, which would be 4 times 4 or 16, we actually add a row of 3 dots and a column of 4 dots. So to go from 3 squared to 4 squared, we must add 3 plus 4 or 7. This is something we discussed earlier. We were talking about the difference between squares, looking at the Pythagorean triples. That was in a previous lecture. And now we see a geometric representation that shows us why this is true. That is, anytime you have a square number, for example, 81 is 9 times 9. To get from 81 to the next square number, we would add 9 plus 10. 9 dots across the bottom, 10 dots in a column down the side, and 81 plus 19, and voila, we have 100, which of course is the next square number. Rectangular numbers are numbers that can be arranged in rows to form a rectangle. All counting numbers are rectangular numbers. And in some cases, there are numerous different rectangles we can make in arrangements of dots of that number of dots. So for example, let's take a look at one example where we have 6 dots arranged in 2 different rectangular formations. We have a rectangular formation that is 3 rows of 2 dots per row, and we also have 1 row of 6 dots. So we have, in effect, a 2 by 3 rectangle and a 1 by 6 rectangle. Now, you may say, well, there are 2 more, and you'd be right. If we turn the picture on its side, instead of having a 2 by 3 and a 1 by 6, we'd have a 3 by 2 and a 6 by 1. And what that tells us about the number 6 is that 6 has 2 pairs of factors, 1 times 6 and 2 times 3. And of course, since multiplication is not dependent upon order, we can write that as 2 times 3 and 1 times 6, or 3 times 2 and 6 times 1. Some numbers, mind you, can only be written in one rectangular way. And here we have 5 dots arranged in one row of those 5 dots. And that is the number 5. And that is the only way. There is no other type of rectangle other than a 1 by 5, unless you want to talk about a 5 by 1, which is really the same thing. The question now is, what kind of number would have only one rectangular manner in which to show it geometrically? We've talked about this kind of numbers. These numbers were known to the ancient Greeks, and of course they're called the prime numbers. So a prime number, geometrically, is a number where you take that number of dots and try to arrange it in rectangular formations. There is only one method to do that, and that is 1 times the number. There is no other arrangement that will use all the dots and form a rectangle. Again, a rectangle is formed when the number of dots in each row is the same for all the rows of that rectangular formation. So we now have another way to present prime numbers. And in fact, in terms of dealing with prime numbers and their importance, we can go back and take a look at young children possibly in kindergarten or first grade, and teach them about prime numbers without ever using the word prime. Allow them to discover, just as the ancient Greeks did, that we can, by arranging things in rectangular forms, that there are certain numbers that are limited in how we can arrange them to only one form, and that is 1 times the number. So the prime numbers can be looked at an early age, geometrically, which would then lead to an understanding at a further time in their education. Some numbers, such as 4, have arrangements that are quite special. Notice the 2 ways to make 4 as a rectangular figure. One would be 2 rows of 2. The second is 1 row of 4. Now, why is this special, you might say? Well, 2 rows of 2 is the same as 2 rows of 2. What's special about that? Well, that is a square number. When you turn that rectangle on its side, you have the exact same picture. So what we have is a fact that if indeed, when you're looking at the rectangular formation of numbers to gain knowledge about the factors, if one of the ways to arrange it is a square, and there will only be one way if there is a square, then that is a square number. So 4 and 9 and 16 in their rectangular formations will have one formation that is square. This leads to an interesting discovery. Prime numbers have only 2 factors, 1 and the number itself. Again, 2 is an even number. Square numbers, by definition, will have an odd number of factors. Take 1. There's only one factor of 1, 1, and 1 is a square number. 4. Well, the factors of 4 are 1 and 4, and of course 2. 3 factors, an odd number. 9. 9 is 1 times 9, 3 times 3. So the factors of 9 are 1, 3, and 9, which indeed is an odd number. 100. 100 is 1 times 100, or 2 times 50, or 4 times 25, or 5 times 20, or 10 times 10. When you write out those factors, you'll find there is an odd number of factors. So square numbers have an odd number of factors, while all other numbers always have an even number of factors, and prime numbers have only 2 factors, and the very special number 1 has only 1 factor. And remember, the ancients thought that 1 was the creator number. So we see that geometry not only allows us to measure areas and volumes, come up with indications about angles and looking at angles in various figures, allow us to do constructions of real-world objects, but also geometry can be used, and in fact was the primary way in which the ancients looked at arithmetic and even algebra. And again, I mention again, that's why I thought 1637 was a very famous year. Once Descartes showed how we could geometrically demonstrate an algebraic function, then algebra and geometry became combined, and sometimes it's difficult to tell when you're doing algebra and when you're doing geometry. In our next geometric lecture, we will talk about triangles and trigonometry.